I'll have this on slideshow. Just please let me know if it will not transition. Okay, so we are now on size comparison for flow reactors. So we will be comparing sizes of flow reactors for the same degree of conversion. Now, what are the factors that we need to consider in designing a reactor? So we have to, of course, number one is what reactor type do we intend to use? Then the planned scale of production, will it be small scale? Will it be large scale? Then the cost of equipment and the operation. So we consider this as well. The safety and the stability and flexibility of operation. Okay, we are now on the second slide. So we are also to consider the equipment life expectancy. So the life of our equipment, the length of time that the product is expected to be manufactured. We need to look into that. How long do we need for the processing, let's say, of one batch? So we need to know that. And the ease of convertibility of the equipment to modified operating conditions or to new and different processes. So meaning, class, if you design as much as possible, your reactor is not as so limiting as to that particular type of reaction only. As much as possible, it should serve multiple use, or can also be used to process other types of reaction. Now, what are the needs to consider, or what are the important needs that we need to look into in selecting the appropriate reactor for a particular duty or a particular objective? So, of course, number one is the engineer have to be experienced enough. Yes, that experience in reactor design. Now, another thing is engineering judgment. So engineering judgment only comes with experience. So as you gain experience in that particular field, in which you are focused on, so you, especially in reactor design, then it's most likely that the design that you're going to come up would be appropriate, shall I say, cost efficient, or has already considered optimization. So as such, if it has already considered optimization, it did not only look into the design of the reactor, but also, of course, the other fields of studies or subjects that needs to be considered in the appropriate design of reactor. So in the start, we have discussed that thermodynamics is needed, heat and mass transfer is needed, together with the other unitary processes that goes along with the design of a particular reactor. Now, the reactor is the heart of the process, we know that, but after we have already produced the product or products, you have unitary processes to do that. Even before the reacting species or materials that need to be reacted are processed inside your reactor, there are still unitary processes that are involved. So this engineering judgment as to what unitary processes should be performed before and after the reaction comes, of course, with experience. Now, the sound knowledge of the characteristics of the various reactor system is also very important. And you are now studying that part, but you are only, actually that includes myself, we are only knowing the introductory part. In the actual setting in the industry, there are actually a lot of things that needs to be looked into that is so different than what we have learned and read from the book. Okay, you will know that when you have your OJT. Hopefully, you will be able to do your face-to-face OJT. And you will know from the engineers themselves in the plant that what they learned from the books, what they learned through their mentors are not enough. So they actually learn through experience. As they say, experience is the best teacher. And then, of course, economics. When you design a reactor, you consider safety, but of course, you also consider economics. So you cannot, kung sa aton pattern pag gusto ka lang design, okay, pwede din na siya technologically wise, engineering wise, it's very good, the design is very good, but it's very costly. But you have to really consider the cost. Because at the end of the day, you cannot operate your business, you cannot operate in the manner that you have designed to operate without earning profit. Okay, so it has to be for a profit. Now, when we go to comparison, if you're going to compare the single reactors with one another, so the batch reactor is only suited for producing small amount of material. They are suited for producing different material from just one piece of equipment. However, class, though this might be a come-on because from just one particular equipment, you can process different sets of raw material, the loading and the unloading of the process system inside the batch reactor also entails cost. So you have to put in your system. Initially, you have to render it uh, ready for reaction inside your batch reactor. Then you let it stand there. And after the reaction has already proceeded, after some time, and you have achieved already the degree of conversion, you take it out. And then you clean it before another different system will be placed inside. So the taking out and the putting in of the raw material takes time. So although the batch reactor can, of course, unless your system requires one very specific design, uh, then you will be needing a different batch reactor, probably with a jacket. The other one has no jacket, depending on the need. Now, for epsilon A equal to 0, this is for constant density system, fluid reacts in the same amount of time for your batch reactor and your plug flow reactor. Thus, take note, same volume for both reactors is needed to do a given job. To do a given job, meaning for the same degree of conversion, the amount of time that your batch reactor can facilitate the reaction to obtain that particular degree of conversion is the same for your plug flow. When is this? When you have epsilon A equal to 0. When you have a constant density system. Now in here we have small instrumentation costs. Oftentimes the batch reactor is just simple. So there's no intricate instrumentation that goes with it. Now, flexible in the sense, we go back to the bullet, the second bullet here, flexible in the sense that you can have different sets of material processed in in a particular kind of equipment or just one particular type of reactor. The downside are the ones here on the red ink. So high labor and handling cost. Again, we go back to bullet number 2. The cost of labor and the handling cost because you need to clean the reactor every time you put in a different system to be processed inside it. Then we have little, if none at all, control on the purity or on the quality of the product. So poor quality control of the product. We don't have much control on the degree of the purity of the product. We just simply put in the system inside the reactor and wait for a certain degree of conversion. But how pure is that? We don't have that much control for the batch reactor. Next is we're going to look into the formulas, the equation that you're going to use for the continuous reactors. And we're going to look into them one again versus another. So this is for the first and nth order reaction. So your tau, your space-time for the MFR for a first order reaction would be this one. For the plug flow would be this one. Actually, what you see here, whether this is for a first order or for an nth order reaction, this actually will work for these two equations that you see here. These are actually performance equations for the two. Now, for any nth order reaction, if you need to consider epsilon A, whether it's a 0 or non-zero, then you have a more detailed specific formula below. For the mixed flow reactor, for an nth order reaction, and for epsilon A, may be equal to 0 or not equal to 0. This is more specific. The formula is more specific here. No need for integration for this formula. Now for the PFR, you could see it in here. Now this one needs integration already. And just like what you have here for the mixed flow, you also have the presence of the epsilon A. And generally, you have the order of the reaction presented as N. So you go back to the performance equations, whether, take note of whether it is the space-time that you want to account between these two, or for these two rather, the MFR and the PFR, or whether it's the size. So whether it's space-time or the size that you want to account for the flow reactors, you won't get lost if you write down first and foremost, before doing anything else in your solution, the performance equation. Because in itself, it's like a map that guides you what is not given and what you ought to first determine before you substitute it on that particular performance equation, whichever of the two is applicable. Now, this one, I got this from, this is even brown now with all this coloring here, because this is from a third edition of Levenspiel. I took a picture of that. So then we don't, it's not common that you have the available soft copy of the third edition of Levenspiel. I don't encourage you to use this graphical approach in determining the size of any of the reactors, may it be MFR or PFR, given another. What do I mean by that? Let's say a problem will give you the size for the plug flow, and correspondingly for the same conversion, you would be asked to determine the size for, let's say, the MFR. Now, this is not graphical, although your answer will be dependent on how well is your sight in using this particular diagram. So in here, on the horizontal axis, you have 1 minus XA. You, of course, need the conversion. That way, you can compare the volumes of the two reactors. Now, why do I say you compare the volume of the two reactors? Because if you notice, class, here on the vertical axis, you have here the ratio of tau CaO raised to n minus 1 for the mixed flow reactor here, and tau CaO raised to n minus 1 for the plug, which is equivalent, so this is the ratio, which is equivalent for the ratio of CaO raised to n V divided by FaO for the mixed, since we have for the mixed flow here, and we have CaO raised to n B divided by FaO for the plug. Now, if we're talking, we have to be talking actually of the same reaction. We're talking of the same reaction, the same degree of conversion, which you need to place in here. You'll be able to get the ratio of the volumes of these two. Now, you may ask me, what about Miss Ali, the CaO here, and the FaO? When we're talking of the same reaction, of course, the CaO for the mixed flow and the CaO for the plug flow will just be the same. So you take it out of there. Of course, their molar feed rates would be the same, because we're talking about the same system. So what is left here in the ratio is just the volume of the mixed flow to the volume of the plug flow. So actually here on the vertical axis, you have the ratio of the volume for the mixed and the volume of the plug flow. This is what you have here. Given the conversion, so you subtract it from 1, you will use the value that you have in here. Now, what about the lines that you have in here? You have actually this same diagram in your handbook. Okay, you can see the same diagram in your handbook. So if it's a first order reaction, you see this one. This is for the first order reaction, and you have here that's dots. And this is for the second order reaction. See this? This is for n equal to 0.5. And this is for n equal to 0.25. So if the order of the reaction is 0.5 and the degree of conversion is 50, so 1 minus 0.5 is 0.5. Now notice that this is class 0.1. And you could count here 1, 2, 3, 4, 5, 6, 7, 8, 9. Rather, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since we start with 0.01, not with 0, so this must be 0.02, 0.03, and until we reach 0.1, because this is 0.09 and this would be 0.1. So then the calibrations here will be 0.2, 0.3, zero point 0.4, zero point 0.5 until you reach 1. The the scaling are not the same. So hindi siya parariho kalagka ang scaling. So going back to my example a while ago, if your reaction is of order n equal to 0.5 and the degree of conversion is 0.5, so 1 minus 0.5, that will be 0.5. So you need to go up, you need this particular line in here because this is for 0.5. And you notice that this is already like wala na siya. So you just have to, let's say, assume that this is going to extend, something like this. Now, if you notice, it will not reach the 0.5. So let's use an example wherein it would be possible for us to use this particular diagram. Let's say the degree of conversion is 0.9. Okay, if it's 0.9, so 1 minus 0.9, or that's 90% conversion, you have 0.1. So you have your 0.1 in here, and this is your order of reaction, which is 0.5. So this is the ratio. This is the point that should give you the ratio of the size of the mixed flow to the plug flow reactor. Now, in terms of the values in here on the vertical axis, it's not also calibrated equally. So you have here 2, you have 3, you have 4 until you reach 10 here. So in our case, if it's for a half order reaction for 90-degree conversion, more or less, this is where we're going to, this is it, and then you're going to read it here. So more or less a little after 2. Okay, somewhere like that. So we say your Vm over Vp is equal to, say, to 2.2. So this is the ratio of the volume of the two. If you know one, then you will know the volume of the other. That the volume of the equivalent reactor, I say equivalent, that will achieve the same degree of conversion. So from in here, you could see, class, that your mixed flow reactor will always be bigger. Than your plug flow reactor because of this multiplier for the same degree of conversion. Now, how do we make, or what other generalizations can we think if for the same degree of conversion, your mixed flow will be able to process a bigger volume, or will require a bigger volume than your plug flow? So we can say then that if you have large-scale operation, and if it's just liquid phase reaction, then you can use the mixed flow reactor because you can process a bigger volume of feed, acquiring still the same degree of conversion as a plug flow reactor. Why? Primarily because of this multiplier that we have in here. It's a given that the numbers that you will generate here in the ratio will be greater than 1. So the volume of the mixed flow will always be greater than that of the plug flow. But of course, if you intend to use the performance equation from one performance equation to another to determine specifically the volume, there's nothing wrong with that. This is just a graph where you can compare sizes for the two continuous reactors, the mixed flow and the plug flow. So this is for n equal to 0.5. This is for n equal to 1. And this is for n equal to 1, epsilon a equal to 2. So this one, meaning dot, dot, dot. And this is for epsilon a equal to 1. This is for epsilon a equal to 0. So the bold lines are for constant density systems, whereas the broken lines are those systems wherein you have a corresponding value for epsilon a. What about if epsilon a that you have solved is not among the lines that you have here? So you just need to approximate. The second group that you see here on top is for second order reactions. This one is for first order reactions. This one is for n equal to 0.5. And this is for n equal to 0.25. Notice for these two, wala na siya maging provide for other values of epsilon. So in here, in this particular figure, you only have for epsilon A equal to 0 for order of reactions less than 1. So kung 1/2 order na siya, wala na siya naghatag pa sa other curves where epsilon has a value other than 0. That's the same thing with n equal to 0.25, or that is 1/4. Now, what is good about this? You don't need to compute because you could see right away the ratio of the two. So if it's a multiple choice thing and you know already the volume of one, then right away, not even consuming more than 10 seconds, you would know the volume of the other reactor. So you'll see this in Levenspiel. If you have a PDF copy of Levenspiel, you'll be able to see it from there. Please check on that and read more on the discussions that goes with this particular figure. Okay? Now, where did I go back? So let me just clear my markings. Now, so the generalizations are in here based on the particular diagram that was shared to you. So for any particular duty and for all positive orders, MFR is always larger than the PFR. Okay, I have repeatedly emphasized this one. The ratio of the volume increases with order. So as we increase the order of the reaction, the ratio of the volume of the mix to plug flow will also be increasing. For zero order reaction, take note of this. This is very important. Reactor size is independent of the type of flow. So if n is equal to 0, the volume reactor size is already independent of the type of flow. So whether you have facilitated it in a mixed flow reactor or in a plug flow reactor, for zero order reaction, it doesn't matter anymore. Okay? When conversion is small, so when XA is small, the reactor performance is only slightly affected by flow type. So if the, let's say, conversion is just 0.3 to 0.5, the reactor performance is only slightly affected by flow type. So meaning the volume ratio approaches unity. There isn't much difference as to the size of the reactor requirement for each of these two. As you can see here, the volume ratio approaches unity as conversion approaches zero. So kung sa aton lingwahe, para hapos maintindihan, kung ang conversion is gamay lang, if XA is small, ang ratio ni VM to VP wala masyado nag-deviate from 1 for conversions, especially near 0. So the ratio increases. What ratio is it referring to? The ratio of the volume of the mixed flow to plug flow very rapidly at high conversion. So the bigger the difference in the size requirements of the mixed flow and the plug flow will be dependent on the XA. Why? Because you could see here, you have on the horizontal axis the needed value of the XA. Now we proceed. So density variation is only of secondary importance to type of flow in design consideration. Why is it only of secondary importance? Because you could see that we only have considered, or the figure have only considered epsilon A for orders greater than 1 up. 1, 2, may epsilon. Pero lower than that, you don't have the epsilon anymore. Meaning, the deviation of the ratio of the two, VM to VP, will not be really that shall I say, pronounced. So, negligible lang siya. Now, as density decreases, in the case of expansion, take note of this, the PFR is more effective than the MFR. As density decreases. So, as epsilon A near 0, it's in the case of expansion, PFR is more effective than an MFR. While as density increases, MFR is more effective than the PFR. Okay, this is when we look into density already. For any given objective or duty, the ratio of the size of mixed and plug flow reactors will depend on the extent of reaction, of course, that's your X sub A, the stoichiometry, the balanced chemical reaction, and the form of the rate equation. So you have the stoichiometric equation, the rate law, and the XA. Okay, the ratio of the mixed to plug flow sizes will be dependent on these three. As for the design application, so we have this particular problem, an aqueous solution, or aqueous reaction rather, of A plus B forming the products with known kinetics, RA equal to 500, C sub A, C sub B, so you have the units there, is to take place in an experimental tubular reactor. Assume plug flow under the conditions that the volume of the reactor is 0.1 liter and the volumetric feed rate is 0.05 liter per minute, with the concentration of the feed given here, both the same for A and B, which is equal to 0.01 mole per liter. Now, what are we required in this problem? So what fractional conversion of reactants can be expected? For the same conversion in letter A, what size of stirred tank reactor assumed mixed flow is needed, and what conversion can be expected for the same size to the plug flow reactor, or equal in size to the plug flow reactor. Okay, so these are our three required information. So we need to please take a picture of the unknown. That way we can discuss, we will have a healthy discussion of the solution. Okay, I'll take also a picture from my end. This is for number 1, sample problem, and this is our required information. Okay, so now with this, we can go to our Jamboard and find the solution of this. Okay, big class. I've been signed out. Why was I signed out? Can you see the Jamboard class? Class, can you see the Jamboard? Are you still there? Do you hear me?
Yes, miss.
Thank you. So if we're not going to finish this, hopefully we can finish in 15 minutes. So these are our given information. So if you took the screenshot, what information can we write here under the given? It's aqueous reaction. You have to be very observant of the description of the reaction. If it's gaseous, if it's aqueous, if it's constant pressure, if it's constant volume, and all those sorts of things. That way you will not miss writing the epsilon A right away. So this is an aqueous reaction, so automatically your fractional change in the volume will be 0. So your epsilon A is equal to 0, and you are provided with the stoichiometry. Okay. Now, it is to take place in an experimental tubular reactor. So, I'd like to place here that this one is to be facilitated in a PFR. And you have the volume. So, volume is 0.1 liter. Feed rate. So, it's liter per minute. So, this must be the small v sub o. It's 0.05 liter per minute. And concentration of the reactants in the feed. So you have equal concentration for A and B. 0.01 mole per liter. Okay? Do you have something to add to this, or this is already okay? So far, everything is already placed in there. So in terms of the required, so what are the required information that you can give to me? Give me one. What's the required information? Letter A. What fractional conversion of reactants can be expected? What is this? What is this? This is X sub A. Letter B, for the same conversion, what size of stirred tank reactor is needed? So we have same conversion as A. You are required for the volume of the mixed flow reactor. And letter C, what conversion can be expected in the mixed flow equal in size to the plug flow? So this time, we have this condition. If V sub M is equal to V sub P, what is the X sub A? Okay? What is the X sub A? This X sub A is referring to this original given information. We're talking about the plug flow reactor. Let me check what is right here. Okay, XA volume of the MFR. That's correct. So now we have written it in here. Do you need to add anything to the information we have written? None? Okay, so we go to the next page. So we go to the solution. Since we are given a PFR, and letter A is asking for the degree of conversion in a PFR, so we're going to write the performance equation for a PFR. So tau, I'd like to place here a subscript P, denoting that's for the PFR, is equal to the integral from CAO dxa over the rate. That would be from 0 to XA. And this is the thing that we'd like to find. Okay? So that's our performance equation for the PFR. Now, what do we need to write in here? We have already the V and the V sub O, so that could give us the space-time. So you have V for the plug flow over the V sub O. In here in our given, so as you will not be mixed up, since it's talking about the plug flow, we write a subscript P in the V. So we have 0.1 and 0.05. So this is 0.1 and this is 0.05. And since, if you notice, this one is in liter and this one is in liter per minute, the unit that we will have here is in minute for the space-time. So I'd like to write CAO outside because it's a constant, and I will have here 0 to XA, and we have dxa, and we have the rate. Okay, you have the rate. Now, can you go back to our reaction? And what would be the appropriate, shall I say, rate law for our reaction? This one. Let me read the problem again. As you are looking at the given information, I will not just change the sharing option. I'll just read the problem. Okay, the problem goes this way. The aqueous reaction A plus B forming the products were given with the known kinetics. So we miss this known kinetics, the rate law, which is 500 CACB. Okay, so we'll go back to that and write here the rate law. So the rate is 500 CA C sub B. It's given. Now, as I was asking a while ago, so we'll write here 500 CA CB. Now, how do we transform our rate law in such a manner that we would just be left with XA as the unknown? What do you do? Before we go to that, can you simplify 0.1 divided by 0.05? What's the answer? So we have 2. So this is 2. And I can write now CaO, and I will have DXA. Now we've known already, class, that whenever we start with equal concentrations, you can see here that we're starting with equal concentrations of A and B, and stoichiometrically we have 1 mole for each, then we can write or simplify or rewrite or transform our rate law in this simplified manner. So I can write it as 500 C sub A squared. Why? So for those who have already forgotten, your CaO 1 minus XA is your Ca. And your CbO 1 minus XB is your C sub B. Your CbO minus CbO XB is your C sub B. I just expanded. This CbO is equal to CaO, right? Because it's just equal for these two concentrations. And from stoichiometry, your CbOXB over 1 is just CaOXA over 1 because it's 1 is to 1. 1 mole of A reacts with 1 mole of B. So then we can change the CbOXB here to CaOXA from in here. So CbOXB is equal to CaOXA. So this is your C sub B. So this is C sub A, right? CaO minus CaOXA here is C sub A. That is why we have it written in this manner. Now we can rewrite this further by writing CaO. You have DXA, you have 500, and you have CaO squared 1 minus XA squared. Okay, so we cancel this one, we still are left with 1 CaO. So we have this CaO here, and this 500 will cross multiply with the 2. So you'll have now 2 times 500 times CaO. Where is it coming from? From in here. The 500 and the CaO, I cross multiplied it in here. That way, you'll be left with the integral on the right side. So you have the integral of dxa 1 minus xa squared. And you have here I'm sorry, class, I was disconnected. So I don't know if we're able to get my discussion. So I'll go back to the Jamboard because we have 3 minutes left. I cannot share with you recording. I'll just find an old recording for this because I was cut. Where is my Jamboard? Here. So this is now where we are. And this is our rate law, original. We change it to this. Further, we rewrite it into this, and this is now what happened. Okay? Now we are after XA, so we just need to substitute all the information. So for CAO, we have 0.1, if I'm not mistaken. It's given as 0.1, 0.01. So this is 0.01. And if this is integrated, the derivative of this is negative, and you will have negative here. And the integral of this would be 1 minus XA raised to negative 1 over negative 1. So this will be gone. So you will simply have 1 over 1 minus XA on the limit 0 to XA. I hope you're getting this, okay? The integral part. So you have to simplify what you have there on the left, then you substitute the limits here. So you have 1 over 1 minus XA minus, if you substitute 0, you will have minus 1. So you'll have here 1,000 times 0.01. Oh, sorry. Yeah, that's 1,000 times 0.01. That would be 10. And this one will go here. So 1 equal to 1 over 1 minus XA. And you'll be able to get the XA. So this one is 11. So your degree of conversion is 0.90. So 0.9091. Check. Okay, 0.9091. Thank you. So this is your degree of conversion for the first question. The degree of conversion in the PFR. Now, using the same degree of conversion for the PFR, determine the volume of the mixed flow reactor. Okay? So if you need to determine the volume of the mixed flow reactor for letter B, you'll have to use a different performance equation. This time, you don't need the integral anymore. And you will have your 100 CA squared. Now, the same tau. So your tau here is 2. So the same tau. But of course, different volume. So your volume of the mixed flow divided by this one, the volumetric flow rate, which is 0.05. So you have 0.05. This is equal to CAO, which is 0.01. Degree of conversion is the same as that for the PFR. You have 500. You have CAO for this, which is 0.01. You need to square it. You have 1 minus 0.9091. You need also to square it. Because this is for the CA squared. CAO 1 minus XA. So you'll get the volume